engineer at Cloudera, where I work on the Kudu project. Kudu, if you've not heard of it, is a new project, relatively new. We released it about 9 months ago. And so today I'll be introducing it, talking about what it does, what it can do for you. So yeah, you can reach me at dan@cloudera.com if you have any follow-up questions. Tweet at me at Dan Burkett. If you want to tweet, make sure you include all the appropriate hashtags and whatnot. So what is Kudu? Kudu is a new storage layer for the Hadoop ecosystem. So in terms of kind of thinking about Hadoop as an ecosystem as a whole, where we fit is at the storage layer, so kind of alongside HDFS or alongside HBase or other key value storage, Cassandra, those style of projects. So we're a little bit below what you're kind of writing your applications on. So typically applications are written towards Spark or MapReduce or whatever. We're at the lower level of the storage layer. We are, I'm going to go into a lot of details about all the features we have. We're Apache licensed open source. We're in the Apache incubator, and we've got beta available. We released about 9 months ago with our first release was 0.5, and we're up to 0.9.1 right now. And I'll talk a little bit about our roadmap going forward as well. So why Kudu? Why did we feel the need to put a lot of resources and build a new storage layer thing? What use cases did we have that HDFS and HBase weren't filling? And it really Kudu is aimed to fill a gap between those two products where this chart on the left here, it has axes and labels and all that stuff, but it doesn't have any numbers, so we like to call it kind of an MBA graph. It's pretty hand-wavy. But on the y-axis we have analytic performance. So how good is your storage at doing big scans, big batch writes, that kind of thing? HDFS tends to do very well with those. And on the x-axis we have OLTP random access performance. So how fast can I insert a row? How fast can I get back individual rows? And HBase, Cassandra, key value store type products tend to do very well at those access patterns. Today, or when we were looking at building Kudu, what we saw was that there's this gap, and there's really no product that can do both. You can do both with HDFS, and you can do both with HBase, but you're giving up a lot of performance relative to their strengths. And so what we wanted to do with Kudu is build one product, one storage platform that could do 80% of the performance of both for both use cases. So that was really the goal. So we wanted high throughput for scans, within a close distance of Parquet on the HDFS, which is kind of the gold standard right now in the Hadoop ecosystem for big analytics jobs. We wanted low latency on single row operations. We wanted database-like semantics, so relational database-like semantics with your typical ACID properties. We're not fully there. We've got single row ACID properties, which means essentially you can't do multi-row transactions. You can't update multiple rows atomically. But we do have we are architected to get there eventually. So that's on the roadmap. Our data model looks more like a relational table, like MySQL or a Postgres, than files. It's not a file system, and it's also not a key value store. So if you're familiar with HBase or Cassandra, there are key value stores, but they also have columns, and you can have kind of an infinite number of columns, sparsely populated. That's not Kudu's data model. Kudu looks much more like relational tables. So you have data is organized into tables. Tables have a finite set of strongly typed columns. With Kudu in particular, you have typed data and a finite number of columns. You can add and drop columns as you go, and it's not a very painful operation, but it is somewhat of a tedious operation as opposed to HBase or Cassandra, where they'll add columns on the fly at the right time. Another thing we thought a lot about when building Kudu is the changing hardware landscape, especially changes in I/O that are coming down the pipeline and have been coming down the pipeline for the last few years. So everyone's familiar with SSDs. More and more we're seeing SSDs in our clients' data centers. They're already prevalent in most consumer hardware that's sold today. And the state of the world is that these SSDs are a factor of 10 faster than spinning disk. And if you don't architect your application to take advantage of that, it's it's going to be a problem. Looking even further down the pipeline is non-volatile memory technology. Intel recently announced something called 3D X-Point, 3D Crosspoint, which is their kind of brand name for this technology, and this is supposedly going to be released sometime later this year. And this is going to be a technology that provides kind of the best of Flash and the best of RAM. So you get almost the random access performance of RAM, but you get persistence like with Flash, and you get, and it's going to be, they say it's going to be almost as cheap as Flash. So that's pretty cool. And of course, RAM is getting cheaper. When we started building Kudu 3 years ago, 64 gigabytes on the server might be standard. Nowadays, 256 is very common. And the whole takeaway here is that I/O is increasingly becoming less of a bottleneck. And so as the I/O bottleneck goes away, other places in your application, other places in your database are going to become the bottleneck, and increasingly that's becoming the CPU. And a lot of existing storage products weren't designed with that bottleneck in mind. So as I mentioned, Kudu is table storage, table-oriented storage. It's meant to be scalable, kind of horizontally shardable. Tested it up to 275 nodes on a 3 petabyte cluster. It's really architected to scale, a lot. So thousands of nodes, many petabytes. It's meant to be fast, millions of read-write operations per second across the cluster. And really what the use case that we're targeting is kind of unlocking applications that need real-time writes. So you have streaming data coming in, but you still need to do these big analytic aggregating scans, joins over the data as it's coming in, which really isn't possible with HDFS today, because you have to kind of batch your writes into files, and that latency might be minutes or hours. Whereas Kudu, as soon as the data comes in, it's available to be read. As I mentioned, we have SQL-like tables, SQL-like data model with faster alter table add drop columns. Kudu itself has a NoSQL API, so it does not have a SQL engine, parser, anything like that built in. So when you use Kudu, it looks much more like an imperative NoSQL API. So you do an API call to do an insert, API call to do a scan, update, everything. But what we've built it is to be a very good layer in order to plug in higher level computation engines. So things like Spark, Impala, MapReduce, all have integrations today, and we're hoping to get integrations across the entire ecosystem so that every kind of higher level project can use Kudu as its storage layer. So I'm going to talk a little bit about use cases and architecture, and then get into architecture. So some of the prime Kudu use cases are time series. So again, you've got real-time data coming in. You want it to be immediately visible. But you're also, when you're doing time series analysis, that's typically going to be a scan operation, right? You're looking at time slices. So I want to look at data over the last hour, over the last month. So that's a big scan. So while you can shove data into Cassandra HBase to do this, and it will keep up with the write throughput quite well, those systems really suffer with the scan performance. Whereas if you were to build on top of HDFS, of course you can't do real-time writes. So that's kind of where Kudu fits in, and it does that really well. Online reporting, you've got data coming in, you want to do big, report-type analytic jobs. One of our earliest production users is Xiaomi, who is a mobile phone manufacturer in China, one of the biggest in the world. And they were basically our earliest production user. I think they've got a production cluster that's around 60 nodes or so, that's doing about 20 billion inserts a day. And this is essentially tracing data or telemetry data for mobile phones that's coming in. So this data is coming in, and I'll show their kind of architecture before Kudu. They've got data coming in batch, and they've got data coming in streaming in real time. So batch data gets shoved up into a seq file. Real-time data gets buffered into HBase. That eventually gets merged with some MapReduce jobs and Spark jobs, where it gets put into HDFS and where it gets put into reports for reporting. The problem with this is it's pretty complex. You have to put your data in two different places before merging it into the final resting place. There's a lot of people that have architectures that look like this because If you have that real-time data coming in, you really have to put it somewhere. The problem is it links to a long pipeline. If you do this well, it's about an hour latency. If you do it really well, you might be able to get it done in minutes, but there's very few people that can do that and have that kind of operational pipeline. Typically, the latency is more like a day. And additionally, if you have data that's coming in out of order, let's say somebody turns off their phone, right, and it's got some batch telemetry data that it wasn't able to send, and then 3 days later the user turns on their phone, the telemetry comes in, well, it becomes very difficult to deal with that out-of-order data with a system like this because the data has already been flushed into HDFS, where it's essentially immutable. So when that data comes out in out of order, you're going to have to figure out some way to merge it in and then rewrite out the results, which can be a very painful process. Kudu manages basically all that stuff for you. So when they moved to Kudu for this use case, they essentially took away the 3 storage things they had and replaced them all with Kudu. And you can see we still got stream processing put in front of Kudu for some of the streaming stuff where you need to do transformations on the data before it goes into storage. But basically all the storage has been condensed into Kudu. It comes in either direct ingestion from their application into Kudu, or it goes through, again, that pipeline. And then straight from Kudu you can run Impala to do your reports or query Kudu directly if you need direct access. So again, this cut down the latency from kind of a best case of an hour to a best case of milliseconds. So like I mentioned, Kudu is really built for integrations. And that's kind of the premier thing, or the primary way that you would interact with data in Kudu. You can go through the NoSQL API, but really most of the time you'll probably be using something like Spark. So this is an example of using Kudu from Spark. It looks pretty much, if you've ever seen Spark SQL code, it looks pretty much like that. You load up a table using a temp table, and then you call your select column A, column B from my table. So it looks pretty much like any other Spark SQL you might have seen. Our Spark connector has been great. It's most of the work on that has been community driven and community written, which has been really great for open source. We have an Impala integration. Impala, if you're not familiar with, is a big kind of NPP style SQL execution engine. So it can do big distributed joins, filtering, aggregation, all that kind of thing. Previous to Kudu, Impala was not able to do inserts or updates because it primarily worked over data in HDFS, and to do a single insert or a single update is pretty painful. But now with Kudu, if you have Kudu as the backing storage for your Impala table, it can do single row inserts and updates. So this is an example create table. And then insert update looks just like a SQL insert update. We've got MapReduce integrations, of course, so Kudu table input output format. That supports all the fancy features. We've also got other things as well. I don't think mentioned on here. We have a Flume integration. So if you're a Flume user and you want to kind of switch out your storage and use Flume to do ETL, you can do that. There's other community efforts going on. Hive, Drill, Presto, Phoenix, all in kind of varying states of maturity. So I want to show a few benchmarks. Benchmarks are hard. I want to stress that if you're interested in Kudu, I really invite you to do your own benchmarks and kind of stand it up and see how it'll work, even a single node and on your data set, because there's no kind of substitute for doing your own benchmarks and seeing how your data and your pipeline work on a storage product. That being said, I'll show some benchmarks. So these are on a 75 node cluster, and we're going to show TPCH, which is the kind of standard, industry standard for OLAP databases, for big analytic databases. There's a query below here. The point of me showing this is not that you'll read the query and understand it, but just show you what an example TPCH query looks like. They're really big queries that join multiple tables, multiple pushdown, or multiple predicates, multiple projections, that sort of thing. It's a 100 gigabyte data set, which is small for a 75 node cluster that fits quite comfortably in there. So we're comparing here Kudu, Impala on Kudu versus Impala on Burkett. So same query execution layer, but different storage. And essentially, what you can see is that Kudu pretty much matches or beats Parquet in most of them. There's a few that Kudu doesn't do as well. And on average, we're a little bit better than Parquet. When the data set size grows, Parquet starts to do better than us. And so I'm not going to claim that Kudu is better than Parquet in every single situation, but we're at least in the same ballpark, and that's where we want to be. I don't have them to show today, but you can also benchmark Kudu we also benchmark Kudu with the YCSB benchmark suite, which is a popular benchmark suite for OLTP big NoSQL databases, and it's about exactly what you'd expect. We do almost as well as HBase and Cassandra. We blow them out of the water on big scans. We don't do quite as well on single row inserts or single row gets, but really we're hitting kind of our performance targets that we wanted to do. We're in the ballpark for both of these systems in their best case, which means we're much better at HBase and Cassandra on scans and much better at HDFS on single row operations. So project status. Like I mentioned, we released it about 9 months ago in September 2015. Most recently, we had our 091 release last week. So we do a minor release every about 2 months or so we release pretty often. We're not saying that it's production ready yet, but we're aiming for a production ready release later this summer or early fall. That'll be a 1.0. So we're having one more, we're going to have a 0.10.0 release, and then shortly after that, we're hoping to have a 1.0. 0.10.0 will be kind of the release candidate for 1.0. We've got a few production users. As I mentioned, Xiaomi is our biggest. Haven't run into any issues. As far as data loss, we had been working on this project for more than 3 years, so even at the time that we released it last fall, it was quite stable at that point. We are part of the Apache incubator. I'm really excited to report we just had the vote passed for us to go to top level status in the Apache incubator as of yesterday. So that was really cool. So it's not done yet, but I think the deal is next ASF board meeting will be hopefully fingers crossed graduating. So that's really cool. A few of our companies that are using us, contributing. And if you want to get started, the best way is to either join our mailing list or to join a Slack room that we have set up. We're very active on that. If you try us out, definitely jump in there if you hit any questions or just want to talk about the architecture or whatnot. We have a quick start VM. We also have RPMs and Debians to install. If you're a Cloudera Manager user, you can do it through Cloudera Manager, which makes it nice and easy. If you want to get started as a developer, you can read our code is of course up on the ASF Git repositories mirrored on GitHub. And that kind of Git history goes back over the last 3 years. So we made everything public even when the project wasn't open. Same with our Jira. So you can go back and see issues from like 3 years ago, which are pretty funny to go back and look at. Back way before I was even involved with the project. And yeah, we definitely encourage contributions. So if you're interested in this project, if you want to help out, we encourage that. If you're looking for more information on Impala and Kudu, my colleague David Alves will be doing a talk later this afternoon at 4:30 in the library. So definitely check that out. And I believe that's all I've got. I've got plenty of time for questions. I can dive, if you're interested more in technical topics, I've got more extra slides on that. So I kind of held those back, but if you're interested, definitely ask.
It sounds like Kudu storage format is not columnar, is that correct?
It is columnar. So that is, I didn't mention this is probably the biggest technical aspect of what sets Kudu and gives a good scan performance, is that Kudu is columnar. And columnar has a very specific definition. I'm using it in kind of the database literature usage of the term, which means that when data is laid out on disk, right, you probably know this, but I want to tell everybody in the room. When data is laid out on disk, all of the data for a single column is written to disk, and then the next column is written to disk, and then the next column is written to disk. As opposed to most databases that you may be familiar with, most popular open source relational databases, MySQL, Postgres, most of the popular key value stores in the Hadoop ecosystem, Cassandra, HBase, all are what's called row oriented. So they'll lay out one row, followed by the next row, followed by the next row. What that means, the practical trade-off is that if you're going to go and get one row, on a row-oriented system, you can seek right to that row and get the row and return it. So it's just a single seek, and that makes a huge difference on spinning disks. For analytic jobs, if you're really focused on doing big scans where you're going to be reading maybe only 2 of 5 columns, but you're going to be reading 1,000 rows of it, it really helps to be in a columnar format because you can not even read those other 3 columns off disk, and you can really efficiently scan through and amortize over 1,000 rows. An extra seek here and there does not make a big difference. So we are columnar, and that's what gives us comparable analytic speed to
Yeah,
Parquet.
I thought so, but then I was surprised when you said that for large data sets, you were somewhat in the ballpark of Parquet or worse off. So what makes you worse off?
Parquet, I mean, it's very hard. So if you've got a big static data set, immutable data set, it's hard to beat Parquet because it itself is immutable and therefore very simple. We have to have a little bit more machinery behind the scenes in order to be able to do single row inserts and updates. So there's a little bit more overhead, but it's pretty close. Yeah. Yeah.
Is it the replacement of HDFS as a complementary to HDFS?
Sorry?
Is it replacement of HDFS or complementary to HDFS?
It is, I would say it's complementary. So, you know, it's not a file system. So if you need a file system abstraction, we can't replace it, right? There's no replacing that. That being said, you know, it does some things that HDFS can't do. So it's got some of the package.
Soon it will be part of the Hadoop distribution.
We hope so, yeah. And one thing I didn't mention is that it has no external dependencies, so it doesn't require HDFS to be installed, although quite frequently when we run it, like with these benchmarks, we use it just like HDFS where we install it on all the nodes. So we actually have HDFS processes and Kudu processes on the same node. And as long as you're not oversubscribing the machine, it works fine. And that's actually how we do all our testing. So Kudu does not rely on HDFS, it doesn't rely on Zookeeper. It has no external dependencies. It looks architecturally somewhat similar to HBase, where you have what we call a tablet server process on every node, and then we have 1 or 3 or 5 master processes that are put on the cluster.
I kept meaning to ask this one on the mailing list. What do the data directories on the master, what is the master actually doing in its data directories versus what like the tablets are doing with their data directories?
Yeah, good question. So I'm going to preface this. I didn't talk about tablets, but tablets are essentially what we call a shard. So you split a table, you've got a very big table, you split it up into say 10 tablets and then distribute those tablets over the cluster. So the question was, why does a master have a data directory? What is the difference between the master's data directory and the data directory that's used by the tablet servers to store tablet data? In the master, we store, actually the master is essentially, if you look at the code, nothing more than a single tablet. And what's stored in that tablet is a listing of all the tables and all the tablets.
So it's basically with the file system metadata, well, the database metadata, I guess?
And those both tables and tablets are kind of limited in size, so that data is typically only a few megabytes.
Got it.
So we have a master, and it's used it's not directly used in the read-write path, but a cold client, when it starts up, does need to go to the master to get locations. And then after that's cached. But essentially, the master has very little data, it's all in memory, and we typically get microsecond responses from the master, so it's really fast.
Can you move the volume query and
Yeah, so the question is about failover and failure scenarios. Can you lose a node and still complete a query? The answer is yes. So we do support replication through the wrapped algorithm, if you're familiar with consistency algorithms. So rapt is equivalent to kind of Paxos. where we typically run our tablets. Tablets are typically replicated 3 ways. So if you have a 5-node cluster, a tablet would be put on 3 of those 5 nodes. If one of them falls over, you can still make progress. And we have to, if one falls over, you can still make progress. If 2 fall over, at that point, you have to bring 1 back online. But if you want fault tolerance to 2 nodes, you can move up to 5 replicas. Yeah.
Do you support indexing like B-tree?
Yeah, we do have indexing. We have a primary key internally, and that primary key is what allows us to do fast single row lookups, as opposed to say Parquet, which doesn't have an index. It's not a B tree under the covers. It's I guess most equivalent to a log structured merge tree, similar to HBase or Cassandra. But but you know, columnar instead of row-wise. Yeah.
So I know that there's a Jira open, I know it's not on the roadmap for GA, for supporting nested types. And I know that you've asked for use cases to kind of see what people want to do with it. I'm kind of curious, like, what implementations are you considering for nested types that kind of, and how is that being shaped by the use cases that you're getting?
Well, so nested types is not actually on the roadmap.
Oh, no, yeah, that's what I meant. It's not on the roadmap.
Right, it's not on the roadmap. So our GA is late this summer. It's not on the roadmap. So we're still very much in the design phase and looking for feedback. It's one of our most requested things, though.
Yep.
You know, I don't have a real answer for you as far as what nested types will look like when you get there, except that it'll look somewhat probably like Parquet.
Yeah, because we're using it heavily with Impala and Parquet, and that's kind of like the one roadblock that's left for us, because like we've been evaluating it, we really like it, but our data is so inherently nested that it'd be, you know, we don't want to have to normalize or anything like that.
Yeah, that's the feedback we've been getting. So it's going to be a high priority feature for sure. But it's difficult. It's a tough one.
Oh yeah,
I mean,
for sure.
it took a long, you know, Dremel to Parquet. Those things are tough.
You have asset transactions?
We do. So we do not have full asset transactions. We have single row transactions right now, and eventually we've kind of designed it architecturally to eventually get there, but not quite there yet. So I mean, but as far as durability, if you write a row, it's definitely that we don't have to write before it's majority of it's been designed to support cross-row transactions. Yeah, so I'll take it outside if there's any further questions.